It is a pleasure to introduce our next speaker, Miahua Jiang. The title of his talk is Sinai-Lully-Bowen entropy, an analog of Boltzmann entropy.
Okay. Well, thank you, Marino, and also William for organizing this session. And yeah, it's convenient. It saves travel time, and especially when I'm getting old and it doesn't really like to travel too much. But on the other hand, it's to me, it's just less interactive. What I'm seeing over here is just Marino. So if you don't mind, I'm gonna request you turn on your video. That way I can see you. Okay. And also
Yes.
I don't mind interrupting me because this is gonna be a very informal talk. I practiced this talk on Thursday with my graduate students and faculty members in the department, and it took me actually an hour. So I'm gonna try to see if I can finish in half hour. Now, Wake Forest is in North Carolina. Actually, for the past 2 years, we were organizing this early semester um, winter, I would say winter camp for PhD students in dynamical systems. And we do expect to have another conference like this next spring. So it's going to be on early January 2027. If you have graduate students, they're interested in dynamical systems, and you can ask them to actually send us information. And Fan Yang is in our department. He is the organizer. This is based on his National Science Foundation grant. So I'm going to start. So this is a very informal one. Okay, so let me see. I need to practice a little over here. I'm going to use single page mode. Yeah, that's right. Okay, so here is the summary, is the abstract. This is really motivated by a conversation I had with Galavotti in 2019. So I was at Lumini, Marseille, and we had a semester-long workshop organized by Mark Polycott and I think also Vianti. And I stayed over there, I think, for a week or two. And fortunately, both Raoul and Galavotti were there. So we were talking about thermodynamic formalism. I'm not sure. Were Boris and Victoria were there as well? That was 7 years ago, nearly. Yeah, okay, that's fine. So I'm gonna explain the connection over here. So really, I want to explain is whether this Sinai-Ruel-Bowen invariant measure, and especially Boris and Victoria also talked about this. So we are going to look at the entropy of this invariant measure and then ask if it can be an analog of Boltzmann entropy. And we will discuss the motivation and also history as well. Mathematical part is minimum. In low-dimensional systems, we have proven properties that reflect the basic postulate and the second law of thermodynamics. Okay. So let me move to the next one. Just a little bit history. So around 1850, and Clausius actually, somehow he was thinking about quantity. It's not energy. And he eventually coined the word entropy. So this actually was told me by Galavotti as well. He was saying entropy, you can see En is like inside, and entropy is from Greek word. It means turning and transformation. So Galavotti was saying, well, this is like an internal motivation to change. So that's the entropy. And Clausius actually wanted this word so it matches energy. So you can, if you put them together, entropy and energy, these are the fundamental quantities in physics. Okay. But Clausius' definition of entropy was defined for system at equilibrium. It's no longer, say, evolving. But on the other hand, he had the concept that when a system is evolving from non-equilibrium state to equilibrium state, the entropy should increase. And that's the second law of thermodynamics, but not from this formulation. So later on, Boltzmann actually formulated this one mathematically. So what he did was that he was looking at the non-equilibrium system. You can think about an ideal gas is enclosed in an isolated place and it's evolving to its equilibrium. And he analyzed collisions among the particles and also other things, a lot of stuff. And then he came up with this so-called Boltzmann equation. And here F is the density function of the velocity vectors. So it has 3 dimensions, 3-dimensional velocity of these particles, lots of them. This is statistical mechanics. So this one over here, FVT, is the density function. In fact, it's normalized. So the maximum value actually is 1. So it's between 1 and 0. And this Boltzmann equation comes from a detailed analysis of physics inside. And we actually know the formula of this quadratic form. It involves F and F prime, but it's a complicated formula. I just want to say it's a quadratic form over here. And this, in fact, if you look at this one, it's an ordinary differential equation, even though it's expressed as a partial derivative, because we're assuming the density function for the velocity, particle velocity, is actually evolving. And then he defined this Boltzmann entropy at that time. So if you look at this one over here, this part is really the density function, and then the logarithm of the density function. Because density function is less than 1, bigger than or equal to 0, so this quantity actually is negative. But Boltzmann actually explained the connection between his entropy and Clausius entropy and concluded in his famous theorem called H theorem that the entropy is equal to negative KB and H at equilibrium. And this KB is the famous Boltzmann constant. And this constant has to do number of particles in certain standard volume over there. And this quantity actually was revised just around 2019. It's a very, very small quantity. Okay, so so if you look at this one, it's the Boltzmann entropy formula over here. Okay. Any questions before I move on? I'm not an expert in Boltzmann entropy, so I had to rely on my co-pilot actually to get all the details. So if you have a different interpretation or a different thing, that's very normal. Okay. All right, number 5, my 5th one. And then there was a gap. Shannon, he was working at the Bell Lab, and he published a paper in their own kind of journal called Mathematical Theory of Communication. He was talking about the accuracy of transmitting these signals through different channels. And he came up with this quantity over here. And if you look at this one, it's very close to Boltzmann's entropy formula. Pi over here is a discrete probability mass function, right? And then you have the log of this Pi. So if this is exactly the same formula, but in the discrete form. He actually derived this formula based on 3 axioms in the paper, and those axioms are pretty straightforward: additivity and monotonicity and things like that. But he wasn't very sure what he wanted to use for this quantity, and then there was a communication between him and von Neumann, and von Neumann suggested to him that use the word entropy. Okay, and here I think I included this Shannon's own recount of this experience, and it's also somehow my motivation. He said, "My greatest concern was what to call it. I thought of calling it information, but the word was overly used. I decided to call it entropy because von Neumann told me you should call it entropy for 2 reasons. One, in the first place, your uncertainty function has been used in statistical mechanics under that name. So it's already has a name. In the second place, and more important, nobody knows what entropy really is. So in a debate, you always somehow have an advantage. But it seems to me that the first one is a legitimate reason, but second one is not really a legitimate reason. How do you think? Okay. So that's another interesting somehow conversation, I would say, exchange of ideas. I don't know exactly the background when Kolmogorov and Sinai actually defined. This is another major transition, getting entropy into dynamical system. But I heard late Anatoly Katak talking about this story many times. And if I'm wrong, I'll get inaccurate. Victoria and Boris can correct me. So, so the legend actually had it that Kolmogorov was thinking of a quantity to describe dynamical systems, complexity of dynamical systems. So he had some vague idea, and then he was working on it. Now, if you remember, Kolmogorov actually designed those three axioms for probability theory. So he was definitely very familiar with this, and he knew Shannon's entropy formula at that time. And Sinai at that time was just early 20s, because paper was published in 1958. Sinai was born 1935. So he was definitely in early 20s, and he was working with Kolmogorov. So Kolmogorov, I think, discussed this with Sinai, and Sinai came up with this process of getting the entropy. The idea of partition, I don't know. I think it was from Kolmogorov, but if you look at this definition, it's very familiar, I think, to most of us. So legend had it that after they discussed this, Kolmogorov was very happy, and he went to Paris maybe to have some kind of thing. And then after he came back, Sinai already had this one. Okay. So if you look at the formula over here, now this is a big transition. It's not for probability density function anymore. It's for a dynamical system. If you have a dynamical system, in general, you can have it for any measurable transformation on the measurable space. But we are focusing on dynamical systems. So you actually partition your space, and then of course, then you have the Shannon entropy over here, but there's no dynamics. And here is probably the idea they got over here. So how can you get this dynamics inside? You just do the preimages and make the partition finer and finer. And in this process, you will capture the complexity of the map. And because now you're increasing the number of partitions, so the entropy is increasing when you do this one. So they say, let's take the average 1 over n and take the limit. And we all know now how to actually prove the existence of entropy. And this is the process, how it was defined. Now, I don't think Kolmogorov or Sinai needed any explanation for why they use this name, because they already knew about this. And also, they were very happy that this entropy is invariant and measurable isomorphism. So they had a paper at that time. I'm not sure if Sinai was on the paper's author's name, but Kolmogorov published this paper in 1958. And if you're interested in this theory, Anatoly Katak had a survey paper of more than 50 pages, and he wrote that paper in 2028, and that's the 50 years of entropy, and he had some discussion over there as well. So, so now so let's look at a little bit over here what's on the slide, saying that this Kolmogorov-Sinai entropy played a huge role in modern theory of dynamical systems, especially for chaotic systems. So we actually can say that entropy greater than 0 implies chaos, and that's why it is actually so important. But then we can ask, what does it share anything with entropy, Boltzmann entropy, other than starting from the same similar formula? Is it kind of, there is some conceptual or functional kind of similarity over there? Number two is which measure you're going to use, because you define the entropy for the map with respect to an invariant measure. Now, for people familiar with chaotic dynamics, there is a natural choice. There is a natural invariant measure, and that's the Sinai-Ruel-Bowen measure. So, and for uniform hyperbolic systems like expanding maps on circle and Anosov systems on torus, Sinai, you need transitive, of course. This HRB invariant measure is unique. So once you have a map, you have this natural invariant measure. Actually, invariant measure is pretty easy to define. You just look at the Lebesgue measure and you pull back the Lebesgue measure using your dynamical system. If it has a limit, that's going to be SRB measure. If it doesn't have a limit, take the average. Not every system, dynamical system, has this kind of limit, but assuming you have an SRB measure, then you're going to call this entropy of the map with respect to the measure of SRB measure, and you call it the SRB entropy. And that way you have one dynamical system and one entropy only. Okay. So, and the connection about whether this SRB entropy can be regarded as some kind of an analog of Boltzmann entropy actually comes from Galavotti-Cohen's so-called chaotic hypothesis. So this is the bridge. They said that if you're looking at a many particle system, thermodynamic system in a stationary state, and you can just say, this is a transitive Anosov system, and then you can study the macroscopic properties. So that's the chaotic hypothesis. So actually, I asked Galavotti at that time at Marseille, and I said, well, you said this is reversible many particle system in stationary state. What if you have a non-equilibrium system? And he said, you also use Anosov system. So that is the motivation that we make actually this comparison. Say, you have a thermodynamic system, and then you can say, I'm going to just match this one with another Anosov system or expanding map. And for Boltzmann entropy, you're looking at the density, this velocity. But for a dynamical system, you just look at SRB measure over there. SRB measure may not have a density, but if you have an expanding map, you do have a density. Most importantly, you in fact have entropy formula I'm going to show you a little bit later. But what kind of macroscopic properties you can look at? You can look at a basic postulate. That means if you start from a non-equilibrium, then after some time, it evolves to equilibrium. And also you can have law of thermodynamics, second one especially, and entropy cannot decrease. So you can try to prove these things for SRB entropy. If you can do that, then of course, then we can actually say it's really close to the functional and conceptual roles of Boltzmann entropy. And if you think about Boltzmann entropy, we have these important properties. First of all, this is the basic postulate saying that velocity is approaching a limit. And this limit density actually is called Maxwell-Boltzmann distribution, which is just three-dimensional Gaussian distribution. And so you have this one. And if you look at, this is second law, because saying that the entropy along the orbit is increasing if you put a negative sign in front of it. So this is the second law. This is the first, not first. This first law is about conservation of energy. This one over here is just basic postulate. And when you talk to statistical mechanics people, they always say Boltzmann entropy is the only reason why the system is evolving to its equilibrium, because the total energy is simply conserved. And just recently, not a long time ago, maybe past decade, and people were able to show that this solution to the Boltzmann equation actually is a generalized gradient flow of the Boltzmann entropy. Because if you assume Boltzmann entropy is driving the system to equilibrium, then entropy should increase in the direction a gradient vector. Otherwise, y is going to increasing, right? There is no other reason. But this is a big problem because it's not easy to define the gradient flow because you need a metric on the space of densities. So this is called generalized gradient flow. But fortunately for our dynamical system, everything goes well. It started with well. So I'm going to explain now the things that we have using, okay, just over here. Using this entropy formula. So if you look at SRB measures entropy, it has a formula. This is the ever famous entropy formula. So rho F is the SRB measure. And then you look at F prime. F prime is the expanding rate, really. If especially in Anosov case, you have the expanding rate along the unstable manifold. You take the logarithm and you look at this integral. And I was talking to Rael about this, and he said, look at this formula. This is just the expected value of the logarithm of the expansion around the manifold. And of course it is. And I never realized that until 2019. That was many, many years after I definitely studied this one. But so this is very, very similar to Boltzmann entropy. It's the expected value of expanding rate. And expanding rate, of course, is a velocity, right, over here. So what we now want to show is that this entropy is the functional defined on the family of uniformly expanding maps. And we actually want to show it has a derivative. It's differentiable. And that's done by Ruel many, many years ago, around 1995. Okay. But recently, I was able to show that you can change the normal kind of CR norm to Sobolev norm and still show it's differentiable. Now you may wonder why we need a Sobolev norm, because then it makes the space of expanding maps to be a Hilbert manifold. And then on the Hilbert manifold, you define this gradient flow, because we know in Hilbert space, you can actually nicely define the gradient vector over there is unique. Okay. And it's not hard, just basic simple mathematics. You can show basic postulate that these maps, this gradient flow, you can actually show its local existence and global existence. Not only that, you can show you start from any map with SRB measure less than the topological entropy, and then it actually converges to the map, linear map, the automorphism, okay? And then reaches the maximum at this automorphism, which is log n for the expanding maps, okay? And you can also show the second law, that the entropy is always increasing. In fact, this entropy, SRB entropy, doesn't have any local maximum. So if you have an entropy that's still less than the topological entropy, it can always find a direction to increase. Okay, so that's the interesting part of it. Okay, so my time is nearly up. I still have 1 or 2 slides. Do you have any questions before I actually go on? No? Okay. So this is actually a simple case, but this is a complete case. Essentially, it's proven completely. You may wonder, what's the next one? Oh, here there's another slide. It's about what's the difference between, say, you follow the entropy, this gradient flow to approach equilibrium, and you also follow the heat equation, because we know that heat equation governs this kind of process as well. And here is the difference that we can see from numerical approximation. So the red one over here is from the heat equation. If you look at the red one, it's a very nice cosine curve over here. But if you look at the blue one, that's the near equilibrium map over there, and it has higher frequency components over there. So when this map approaches equilibrium, it's not following the heat equation. So whatever gradient flow we have, it's not from heat equation. And I was able to find a partial differential equation closely connect to this one. If you look at this one over here, if you don't have this denominator, then it's the heat equation, but it has so-called a gradient-dependent heat equation. This is also diffusive equation over here, okay? If you're interested in this topic, there is a recent paper published in Communications of Mathematical Physics under the title of Gradient Flow of the Sinai Roelle-Bowen entropy. Okay, I think that's pretty much all. And here are the extensions. We could extend these things to Markov transformations on a closed interval, low dimension still, and transitive Anosov map on two torus. Okay, and also families of expanding maps of transitive Anosov, but we only have the local existence, only the local existence. There is no global existence. So if you allow me, actually, I would propose a open problem over here, saying the following thing. Just look at the Anosov systems in open component, say, containing one automorphism over there. And you look at the HRB measure of the perturbations inside this open component, assuming that the entropy isn't really the maximum, which is the topological entropy of the automorphism. Then you ask yourself, if you perturb your Anosov system, can you always gain some kind of HRB entropy? If you can, that means you are proving the second law of thermodynamics. It means a system at non-equilibrium will always try to evolve along the path of entropy increase. Because I just had this problem when Boris and Victoria were talking about their topics. So I don't have it formulated completely, but I can actually share it with you. But I think also this video is available. You can probably just figure out what I was saying. Okay. In the context of hyperbolic iterated function system, yeah, the uniform hyperbolicity is really needed. Otherwise, you don't really have the differentiability of this HRB entropy. So you need something basic. You need to have a unique HRB measure. And also you need this entropy to be dependent on your underlying map actually smoothly. So these were the things that's done by earlier people, Roelle especially. And also you need to show that this entropy actually varies when you are perturbing your system, because otherwise your entropy isn't changing, right?
Okay, okay.
No, thank you very much.
Yes. Any question?
Thank you for the nice talk.
So you have a question, right? Megha, you have a question?
Megha posted her question in the
Yes.
chat. I'm not
I
sure if
have
you can.
already posted my question in the chat box.
Yeah. Did I answer your question?
Yes.
Okay, thank you.
Okay. Any more question? If not, let us thank the speaker again. So our next talk will start in 1 minute.